Okay, so once again, isotopes, besides being Homer Simpson's baseball team, are atoms of the same element that have different mass numbers because they have different numbers of neutrons. Okay, remember, if we change the number of neutrons, we're going to change the mass. So, for example, carbon. If you look at your periodic table, and you'll see the atomic mass for carbon is possibly 12.01, depending on the periodic table you have. Some are a bit more specific. You might see 12.011. Okay, that's an average mass. We'll talk about that in a minute. Carbon can have, well, first of all, okay, how many protons does carbon always have? Well, it's atomic number 6. That means it's always going to have 6 protons. So for all of these carbons, carbon 14, carbon 13, carbon 12, it's all carbon, so it's all going to have 6 protons. What's changing is the number of neutrons. So if the mass number is 14, how many neutrons are there going to be? Would have to be 8, so that they add up to 14. Carbon 13, 7 neutrons, and carbon 12, 6 neutrons. Okay, now because the average mass number is 12.011, you can figure out that most of the carbon is carbon 12. Most of the carbon on the planet is carbon 12. But we do have some carbon 13 and some carbon 14, so if you average it all out, you're going to get a decimal. Okay, so this number with a decimal is called the atomic mass, and it is the average mass number for all the naturally occurring isotopes of an element. Now it's interesting to note that these are actually changing. We're updating the periodic table with 20 new atomic masses because we made some mistakes in our calculation before. Okay, so students often get confused between the atomic mass, which is the average, and the mass number, which is for a specific isotope. Okay. So, for example, hydrogen. Okay, hydrogen. If you look on your periodic table, you'll see it has an atomic mass of 1.01. Okay, so from this you can assume that most hydrogen is hydrogen 1. Okay, which is one proton and 0 neutrons. But you can also find hydrogen 2 and hydrogen 3 even. Okay. So the Bohr model, we've talked about this already in a previous video. We find the electrons in specific energy levels or shells within an atom. We can represent these shells as rings around the nucleus. The further away the electrons get from the nucleus, the higher their energy. Therefore, shells closer to the nucleus contain electrons with a lower energy. And electrons don't have brains and they don't really want to do anything, but it's helpful if you imagine that they want to be at the lowest energy possible. So that they're going to start, if we're filling up the shells with electrons as we draw these things, we're going to start with the innermost shell. Okay, but there is a maximum number of electrons that can fit in this shell. The main reason for that is that the electrons don't like each other. They repel each other because they both have negative charges. So you can only fit 2 electrons in that first shell. The second shell is further from the nucleus and has a bit more space, and it can hold 8 electrons. And in the next video we'll finish this up and we'll do a couple of examples.